Okay, in this example, we're asked which nozzle will fill the tank faster, or will they fill at the same rate, assuming that the tank is initially evacuated. So it's initially a vacuum inside these tanks. The upstream stagnation properties, throat areas, and tank volumes are identical in both cases. So the P0, T0 are the same, throat area is the same. The only real difference here is that this is a converging diverging nozzle, and this is just a converging nozzle. So we're asked to find which one will fill the tank faster. So an excellent question and a good conceptual question. The answer is actually that the converging diverging nozzle tank will fill the tank faster. And the reason for that is because it stays at choked flow conditions longer than the converging nozzle. So let me sketch this out for you. Let's start with the converging nozzle. If I plotted the pressure, let me just sketch this out and then I'll describe it. Let me finish sketching it all out. Here's the throat. What I'm doing is I'm plotting the pressure in the tank as the pressure as a function of position. X here is just this position like that. And I'm plotting the static pressure to stagnation pressure as a function of position inside that nozzle. And for the converging nozzle, you'll see that the flow reaches sonic conditions at the throat for quite some time until the pressure there is equal to P star over P naught. At which point, if the pressure is higher than this P star, then the flow will become unchoked. Okay, so remember that the Mach number is 1 here. The throat. So if I continue this plot beyond the throat, so when it starts off initially, initially the tank is evacuated, so the pressure inside the tank would be very close to 0. Down here, the flow would be subsonic in the converging section because we're starting from stagnation conditions. It'll be subsonic here. Can't reach sonic or supersonic conditions unless it hits a throat, right? So the throat's right there. So it initially would be choked. You would reach a Mach number of 1 here because the back pressure is much lower than P star over P naught. And it would continue that way as the tank fills. And then eventually we reach a point where the tank pressure is equal to P star. So this would be when the flow is just on the edge of no longer being choked. And then if we went for, as the tank continues to fill, then the flow would actually be unchoked. It would look something like this. Here, the Mach number here at the throat would be subsonic. And then it eventually continued to fill until we reached stagnation conditions everywhere, where the pressures equalize between the exterior and the interior of the tank. So basically we would have choked flow conditions. The mass flow rate would be m dot choked during this entire range of pressures here. So as the tank continues to fill up until the back pressure is equal to P star, we would have choked flow conditions. And keep in mind that the choked flow mass flow rate is a function of the stagnation pressure, and I can't remember the full formula. I don't remember exactly what the exponent is here, but it looks something like this. Just going from memory here. So the choked mass flow rate is the highest mass flow rate that you would have, and it's a function of the stagnation pressure and stagnation temperature, which remain constant here. And A star is, of course, the area of the throat because it starts off at choke conditions, so the Mach number at the throat would be 1, so the throat area and A star would be the same. So you'd see that you'd have choked mass flow rate all the way until the back pressure equals P star for the converging nozzle case. Now let's go ahead and sketch it out for the converging diverging nozzle case. And this one's more complicated. It'll take a little bit longer to sketch it out. So we have the throat somewhere in the middle here, and this would be the exit. And we would get plots that look something like this. So hopefully you've seen these kind of plots from the course notes. just the different kinds of conditions you can have in a converging diverging nozzle. This pressure right here, this is the pressure at the throat. This will be the P star over P naught. Now here we would have choked flow conditions for all of the cases that I'm going to highlight. So we're starting off the back pressure. You know, the pressure in the tank is basically at a vacuum, so it's way down here. So we have what's called underexpanded conditions. So the underexpanded conditions case goes, we have subsonic, we start from stagnation conditions, the flow is subsonic. In the converging section, it'll be sonic at the throat, goes supersonic in the diverging section, and then it goes through this kind of complicated set of expansion fans and oblique shocks outside the exit. It would all occur in here inside the tank. And that's what we call underexpanded conditions. But the important thing is that we will be at choked flow conditions because the pressure at the throats, the sonic pressure, the Mach number there is equal to 1. And our mass flow rate would be this choked mass flow rate. Okay, it would still be the same P naught, same T naught. Remember, these are the same. And the A star is the same because the throat areas are the same. So we'd have the same mass flow rate as the choked mass flow rate for this set of conditions. And then as the tank pressurizes, we'd eventually reach the case where we have design conditions or perfectly expanded conditions where the back pressure and the pressure right at the exit are exactly the same. It's still supersonic here. The flow's still choked. And then as the back pressure increases, we'd go through an overexpanded case. It's still supersonic here, still have a Mach number of 1 at the throat. It's just at the exit, we have supersonic conditions, and then it goes through oblique shocks and expansion fans until we reach the back pressure. Then we'd have this case here where we go through, we go subsonic, sonic, supersonic, and then hit a normal shock wave somewhere in the nozzle. Then it goes subsonic. This one is still, that case is still a choked flow case because we have a Mach number 1 at the throat. And then the critical case is this one. I'll highlight this one in a slightly different color. It's this one. And this one, what happens is the flow is subsonic, reaches sonic conditions at the throat, but then goes back to being subsonic till the exit. And then it's subsonic at the exit, and the exit pressure and back pressure are the same. When we have a back pressure that's higher than this pressure right here, if the back pressure is a little bit higher, then the flow becomes unchoked, and it would look like this one. I'll draw it in blue just so it's a little clearer. So this one is unchoked. The Mach number here would be subsonic. Okay, so the key thing that I want to highlight here is the back pressure at this case, right at the critical case where the flow just becomes unchoked, is higher than P star over P naught. You see the back pressure is higher than this P star value. So our converging diverging nozzle case will stay in a choked condition for a higher back pressure than the converging nozzle case. See, the converging nozzle case stops being choked when the back pressure is equal. Let me highlight it in the same color. It'll be in the choked case until the back pressure is equal to P star. And then it becomes unchoked after that. But for the converging diverging nozzle case, the flow will become unchoked when the back pressure is higher than P star. So that means that the converging diverging nozzle case can fill for a longer period of time at choked flow conditions, so it'll fill up faster than the converging nozzle case. So in the end, the answer to this is that it's the converging diverging nozzle case that will fill faster than the converging nozzle, and the reason is that it's because the flow remains choked to a higher back pressure than the converging nozzle case. Okay, so if you can understand this example, then you have a pretty good idea of the differences between flow through a converging diverging nozzle and flow through just a converging nozzle. So we'll go ahead and end the example there.